Can you apply arithmetic mean method in this scenario for estimation of missing rainfall data? If you are in doubt, then this video is for you. Do you know what will happen if you apply normal ratio method for a case where all the neighboring station normal rainfall values are below 10% of target station normal rainfall value? Today, we will discuss the challenge of handling missing rainfall data by using GeoGebra to get intuitive feeling about formulas. Hydrologists rely on time series data to run computer models. However, gaps frequently occur within these datasets. Most hydrologic models do not permit gaps in time series data. Those that do allow gaps will either infill missing values using internal estimation methods or introduce significant errors into their predictions. Accurate rainfall data is vital for flood prediction, agriculture, and climate studies. But when data has gaps, estimate of missing data help in reliable prediction by maintaining the continuity of data. First, let's discuss in what situations rainfall data becomes missing. Well, sometimes, despite the best efforts, rain gauge may develop faults leading to gaps in data collection. Other possible causes for gaps are: data is incomplete due to technical issues like calibration and blockage. Sometimes the rain gauge is functional, but it is inaccessible for a short period, maybe due to road closure. In situations like wars, which is currently undergoing in many parts of the world, collection of rainfall data becomes secondary. So, the key point is that it is a temporary problem. Data is missing for short period, for example for a week or a month or a year. As you can see here, data is missing for July month only. Otherwise, rain gauge is functional and accessible for all other times. So when this happens, it becomes necessary to estimate the missing data to maintain a continuous, complete, and reliable hydrological record. There are two major techniques to estimate missing rainfall data. 1. Estimate based on use of long-term data, that is, historical data of same rain gauge. 2. Estimate based on concurrent data of neighboring rain gauge stations. In this video, we will use second technique only, that is, by using neighboring rain gauge stations. Before exploring the methods, let us define some essential terms. Target rain gauge station. This is the station for which the rainfall data is missing. We will denote this station as X and its missing precipitation value as Px. The normal annual precipitation for this target station is Nx. It is usually known from historical records. So, what is normal? In engineering, normal is also defined. For example, normal rainfall is the average rainfall over a period of 30 years. When yearly totals of rainfall are averaged over a period of 30 years, we call it normal annual rainfall. We also use term normal monthly rainfall. If monthly totals are averaged over 30 years period, similarly, we can define it for particular week or specific date also. The second concept is index stations. These are neighboring stations to the target station that have complete rainfall data for the period in question. Typically, 2 to 4 index stations are selected, but how do we select these stations? In general, locations closer to each other tend to have more similar rainfall patterns than locations farther apart. This is due to weather systems being large and spatially continuous. However, this may not be true for mountainous region. The number and distance of index rain gauge stations required will depend upon rainfall variability and the geography of the area. For example, on the windward side of hills, there is a lot of rain and very less on the leeward side. In a situation like this, we have to take neighboring rain gauges on one side of mountain only. In this case, on windward side only, as target station is on windward side. For a plain area, rain gauge should be near the target station, evenly spaced, and should have concurrent record. We can divide surrounding area into 4 quadrants and select 4 stations, preferably one on each of the 4 sides. Here X is the target station and 1, 2, 3 and 4 are index stations. P1, P2, P3 and P4 are the recorded precipitations at these index stations. Normal annual precipitations are N1, N2, N3 and N4. We will discuss 4 different methods of estimating missing rainfall data based on concurrent data of neighboring rain gauge stations. We need to understand the suitable conditions for the application of these methods. While these methods produce same result under uniform conditions, their performance varies significantly when conditions differ. Let's discuss each method one by one. Method 1. Simple arithmetic mean method. It calculates the missing precipitation at the target station by simply averaging the rainfall recorded at the surrounding index stations. Px is estimated as summation of Pi over m, where I varies from 1 to m. M is total number of index stations and its value can be 2, 3 or 4 as shown here, depending upon how many index stations are chosen by hydrologists. We can see that each index station is contributing equally to the average, that is 1 over m. Let us do an example. The normal rainfall of 5 rain gauge stations A, B, C, D and E are 137 centimeters, 125 centimeters, 102 centimeters, 76 centimeters and 113 centimeters respectively. During a particular storm, the rainfall recorded by stations B, C, D and E are 13.2, 9.2, 6.8 and 10.2 millimeters respectively. Estimate the rainfall at station A during that storm. Let us write this data into tabular form. Station A is the target station for which the storm rainfall is missing. Its normal annual rainfall data is known 137 centimeters. Stations B, C, D, E are the 4 index stations for which storm rainfall and normal annual rainfall for that period is available. Note the units here. Normal rainfall is in centimeters and rainfall for a particular day is in millimeters. Let's solve this in GeoGebra. The advantage of GeoGebra is that it has sliders which can help in the visualization. M is 4 here, so the formula becomes like this. The calculation yields an estimated value of PA equals 9.85 millimeters. Each station has equal weight or 0.25 in this case. So when we change rainfall value using sliders, you can see the contribution changes in the formula and in the final estimate. The advantage of this visualization will become more evident in the normal ratio and other methods. In 1952, researchers found that the simple arithmetic mean was often unsuitable for mountainous or topographically diverse regions. They proposed a more robust method based on the ratios of normal annual precipitation at the target station to normal annual precipitation at index stations. For 4 index stations, Px is estimated as 1 over 4 P1 nx by n1 plus P2 nx by n2 plus P3 nx by n3 plus P4 nx by n4. If we take nx as common, then formula in general can be written as Px equals nx by m summation of Pi by Ni, where I varies from 1 to m. You can write the formula in any of these ways. Whichever way helps you remember it best. The authors also showed that if the normal annual precipitation at all index stations, Ni, lies within 10% of the normal annual precipitation of the target station Nx, then the simple arithmetic mean method should be used. Otherwise, we should use the normal ratio method. This criteria of 10% was decided on the basis that if all Ni lies within 10%, then there is not much difference in the result between the normal ratio and simple arithmetic mean method. We will visualize this in GeoGebra. Let us apply the criteria to the example which we have discussed earlier. Here NA equals 137 centimeters. We can find NA plus minus 10% of NA, which will give us range from 123.3 centimeters to 150.7 centimeters. Now we will check whether normal rainfalls at station B, C, D and E lie within this range or not. We can see that here 125 centimeters, which is normal rainfall at B, lies in this range. The rest of the values lie outside this range. So the normal ratio method should be used. We'll go to GeoGebra and apply the formula for normal ratio method. These sliders are of normal values, which we will use later. Firstly, put the values of normal and storm precipitation in the formula. We will get estimate of PA equals 12.86 millimeters, which is different from estimate by arithmetic mean method, which was 9.85 millimeters. This is because weight of each index station is different. In case of arithmetic mean method, all weights of index station were same, that is 0.25, whereas here the weights of each index station are modified by normal ratios. We can see that for station D has weight of 0.451, which is the highest among all the index stations. This is due to least amount of normal rainfall for station D. It means percent contribution of selected storm at this station to its normal rainfall is large for this day, and therefore station D's recorded data heavily influences the estimated value of PA. Now let's use sliders for changing the normal values of NB, NC, ND and NE so that their values lie within range, that is between 123.3 to 150.7 centimeters. You can see that the estimate of storm rainfall approaches 9.85 millimeters, which was estimate of the AM method. The estimate will be exactly 9.85 millimeters is rainfall at all index station and target station is same, and weights will become equal to 0.25. In this case, all the normal ratios will be equal to 1 and formula will reduce to arithmetic mean method. If variation of normal rainfall at index stations is less than plus minus 10% of normal rainfall at target station, then the effort required to use the normal ratio method does not yield any better results. Let's summarize what we have done till now. In the introductory section, we explored techniques to estimate missing precipitation data. First, we looked at why data goes missing. We defined key terms like target station, index stations, and normal rainfall. Next, we explained how to select index stations. In next section, we introduced the simple arithmetic mean method and solved a GeoGebra example. In this section, we covered the limitations of the arithmetic mean method. We introduced the normal ratio method formula and demonstrated its solution in GeoGebra. We examined the variable weights of index stations. We also explained the 10% criterion. I hope now you will be able to understand why we avoid normal ratio method when normal values at index stations fall within 10% of the range target station. In this section, we will explore two spatial interpolation techniques, inverse distance weighting and the modified normal ratio method. We will solve the same example which was discussed in earlier two parts in GeoGebra. Both these methods require distance from each index station to the target station. Here, D1 is distance of index station 1 from target station X. Similarly, we can define distances D2, D3 and D4. Modified normal ratio method require normal precipitation values at index stations in addition to distances. First, let's examine inverse distance weighting method. IDW assumes that neighboring stations closer to the target station exert a stronger influence on its rainfall depth. Px is estimated as summation of Zi Pi, where I varies from 1 to m, over summation of Zi, where I varies from 1 to m. The weighting factor Zi for each index station is inversely proportional to the square of its distance di from the target station. Let's go to GeoGebra. We can rewrite the formula for estimation of PA so that we can observe the weights in GeoGebra. We will change the distances using sliders and will observe its effect on the weights and PA. Initially, let's keep all the distances as same. We can see the weights are 0.25. These weights are same as arithmetic mean method, and estimate of Px is 9.85 millimeters, which is also same as arithmetic mean method. Notice how the influence of station B increases as we move it closer to the target station. This is indicated by increase in weight of index station B from 0.25 to 0.46, and rest of the weights become 0.18. This means that precipitation of station B has more influence on estimate of station A than the rest of the stations. Additionally, if we change distance AD to 5 kilometers, both index stations B and D have equal weights, as both distances AB and AD are same. In summary, we can think IDW as improvement over arithmetic mean method. This method is applicable for plain areas. If surrounding stations experience significantly different long-term precipitation due to elevation or microclimates, which means normal rainfall of neighboring station will be different, modified normal ratio method is good option. MNR combines normal ratio with IDW weighting method. It incorporates each index station's normal annual precipitations as well as distance weighting factors. Px is estimated as Nx summation of Zi Pi by Ni, where I varies from 1 to m, over summation of Zi, where I varies from 1 to m. Let's visualize MNR in GeoGebra. We will use the same example which we did earlier. We will use these sliders for changing distance and these sliders for changing normal ratio. At first, we can keep the distances same. We can see that the weights of each index station and estimate of PA are exactly same as normal ratio method. Now, if we change the distances, we will get new estimate of PA, which is unique to MNR. Let us summarize. Inverse distance weighting method is better than a plain average because it trusts nearby weather stations more. The closer a station is, the more its data matters. Modified normal ratio is better picked for mountains and uneven ground because it looks at two things: how close the station is and how much rain that area usually gets. Now, let's visualize all four estimation methods for missing rainfall data simultaneously in GeoGebra. Scenario 1: Introduction and Baseline Scenario. We are looking at an interactive GeoGebra simulation to visualize how different methods estimate missing rainfall data at station A using surrounding index stations B, C, D, and E. In our initial baseline scenario, every index station is located exactly 8 kilometers away from station A. Every station, including station A, has an identical normal rainfall of 100 centimeters. Notice that under these conditions, every single estimation method, simple arithmetic mean method, normal ratio method, inverse distance weighting method IDW, and modified normal ratio method MNR yields the exact same result, that is 9.85 millimeters. Why does this happen? When the normal rainfalls and distances across all surrounding stations are uniform, the formulas for NR, IDW, and MNR all mathematically reduce straight down to the simple arithmetic mean. Scenario 2: Varying normal rainfall. Now let's adjust the parameters using our GeoGebra sliders. Keeping all distances constant at 8 kilometers, let's change the normal annual rainfall values to the example which we solved earlier. NA equals 137 centimeters. NB equals 125 centimeters. NC equals 102 centimeters. ND equals 76 centimeters. NE equals 113 centimeters. Observe what happens to our estimates. For simple arithmetic mean and IDW estimate remain unchanged at 9.85 millimeters. Because all stations are still equidistant, IDW exerts equal weight on each station, behaving just like a simple average. For normal ratio and modified normal ratio, estimate adjust to 12.86 millimeters. Because both methods incorporate the unique normal annual rainfall ratios between station A and the index stations, they yield identical estimates. Scenario 3, varying distance and normal rainfall. Finally, let's change the distance of station B to 5 kilometers using the AB slider while keeping the other stations at 8 kilometers. Now, with both normal annual rainfalls and spatial distances varying, every method responds differently. Simple arithmetic mean stays at 9.85 millimeters. It ignores distance and normal rainfall completely. Normal ratio method stays at 12.86 millimeters. It accounts for normal rainfall but not spatial distance. Inverse distance weighting method increases to 10.79 millimeters because station B is closer, giving its recorded precipitation 13.2 millimeters, a higher weight. Modified normal ratio method adjusts to 13.31 millimeters. MNR combines both spatial proximity represented by distance and historical climate data represented by normal rainfall, giving us the most comprehensive estimate among the four methods. This visual demonstrates how spatial distance and normal rainfall directly impact estimation method. Which topic in hydrology do you think should be covered in the future videos? Let me know in the comments below.